So when we do not have the uh, let's say the knowledge about our active site, uh, right, of the target protein, uh, in our previous studies that we have done, or previous example, we know that the drug molecules was co-crystallized with the active site pocket, right? So let's say we do not have this information, we just model the protein, like in the case of Bepsipen. Okay, Bepsipen. Okay, we model the protein, so we do not have any information about the co-crystallized ligand. Essentially we do not know that means that we do not know the active site pocket, right? So in order to predict the active site pocket, or to do the targeted docking for this unknown protein, or the unknown active site protein, we can do binding site or active site prediction. Okay, so we we, we can divide or classify this binding site prediction into two ways. So ligand specific, so these are like tools, but most of these tools are now old and it's not working. Okay, so but anyway, just for your knowledge, it can be divided into like this. So these are the tools that are specially designed for identifying metal binding sites, and then iron binding sites, and so on. Okay, so this is ligand specific. Okay, but we can have also global method. In the global method, we can go by sequence base or structure base. When you are saying sequence base, it is looking for sequence similarity. Okay, from that other comparing with other uh, sequences. Okay, so they are looking for conserved region, and when you find this conserved region, this may be a domain, right? So this particular region, what kind of function they do, according to that they can just tell that this specific region may be your binding site. Okay, because it perform this kind of function, and this have some kind of pattern which is conserved for in all across the uh, evolutionary, it is conserved across all these organisms. Okay, so like that you can go for this sequence base. So concavity is one of the tool, but still when I tried, it is also not working. And you can go for structure base. Okay, so in the structure base you are looking for protein prediction based on the structure, active site prediction based on the structure. So again, structure based, you can divide it into pocket based or template based. So when you say template based, here we are looking for sequence, and then trying to find domain, and then what kind of function. So according to that function, you can say that from here to here it can be the protein active site, or the binding site of the particular target that you are looking for. So in the case of structure base, you are looking for 3D structure. So in a template base, they are looking for similar structure. So you have built this homology model, right? So when you go for searching in a structure database, you see you are trying to overlap this structure and see what are similar 3D structure present in the database. So obviously if they are uh, similar in their structure, means they may be evolutionary related or homologous. Okay, if the structure that are present in a database has already defined active site, let's say you have co-crystallized ligand in the database structure that you are comparing with your target structure. So if they have this co-crystallized ligand in this particular site, when you overlap this structure, your target structure, so that position of your target structure may also be the active site pocket. Okay, this is how the concept is for the template base. So Probis is one of the uh, program to do that. Okay, so again, when you say pocket, just someone is messaging, just a second. Okay, so when you say pocket base, you are trying to find the uh, cavities or pocket on the protein surface where the binding of the ligand are likely. Okay, so you can go for a geometry base. So in the geometry base, you will be looking when you say pocket, you can have different kind of pockets, right? So you are looking for those region in the protein where there are some pockets, okay, or cavities. Okay, so based on the size of the pocket, uh, then depth depth of the pocket, or the shape of the pocket. Okay, so they will be looking for different kind of pockets in the geometry based active site prediction. Okay, so the F pocket is one of the tool to do that. Using this implement this geometry based active site prediction. And then dog site scorer is also one of the tool. Okay, we'll be using this dog site for pocket or active site prediction. Okay, and when you say energy base, what they are doing is you have this okay, for this energy base you have this protein surface. Now you are taking some kind of probe, okay, some kind of let's say a fragment of ligand or something, some kind of probe you are taking, and you are checking what kind of interaction you are having here. Okay, so they are just trying to see on the surface of the uh, protein molecule or your enzyme. They are trying to see what kind of interaction they are having. So based on that energy that you find from the interaction, it can be through van der Waals, can be through hydrogen bond or electrostatic. They're trying to see which region of the this protein are having high energy. Okay, high binding energy. So those regions where there are high binding energy, that may be the active site pocket. Okay, so this is empty site does that. So it's they do combination of things, but one of the method they use is this energy based pocket or prediction. Okay, so let me go to this dog site scorer, okay, and see how we can predict. And we can also see Probis. Okay, Probis takes time, so I already have calculated or done the prediction for the enzyme or the cysteine protease enzyme that we did yesterday for model building for yesterday's work. Okay, so so let me just I'll just show you the Probis how it works. So this is the results of Probis. Okay, and it looks something like this. Okay, so let me share the address. So here you can upload the structure. So in our case, I think let me go back this one and then homology modeling, right? So out of this structures, you can take one of the structure and do. But AlphaFold was giving better, I mean, score for the models. Okay, when we did model validation. So let's take AlphaFold. Okay, and that's it. So this will be chain A, one chain only. So you can just submit, and after submitting it will run for about 1 hour or something, and you will get a result like this. Okay, so this is your, this structure is your query protein, and you see these are the they are doing a template search. Okay, so this protein structure, they're searching against a database. So after searching the database, they are comparing and see which are the ligands or the inhibitor that are present uh, in the particular corresponding uh, database molecule. Okay, so this is the PDB ID of some database that is having similar structural conformation as the our target molecule. Okay, and when you say view 3D, it will show uh, the the ligand molecule that was co-crystallized with this database molecule. Okay, so again, if you do show 3D, another molecule will come here. So this is how they have binding at the similar site. So you see, you can see that most probably because these are homologous protein, they are very much similar in their 3D structure arrangement. So in your target protein also, maybe the binding site will be around here only. Okay, so at this region. So you can take this information, you can go back to this PDB ID, download it, and you can open Mastro, overlap them and see where is the position for this particular ligand, okay, in your target model. So anyway, this is how you can also check, but let's go to that. Okay. So let's do one more with this geometry base. Okay, so you will go for dockside scorer. So the idea is all the same. Even if you do for structure based, template based, they will give you different option for you to choose. Okay, so geometry based will also give you all the cavities. Okay, because they are looking for pockets, right? So all the pockets, so out of which pocket you have to choose, that you have to decide. Okay, based on your study. Okay, so energy based also, they will give you different pockets. Okay, and which pocket is suitable for you, you have to decide. So I will tell you how you can decide. So let's upload our protein. So let's go for AlphaFold and click go. So here is the dockside scorer. Okay, so you choose this option or the program and then click dockside scorer. So you keep the default and then click calculate. So after getting this particular pocket or calculated pocket, let's do docking. Okay, let's do docking using the automated one. Okay, so let's go to that working folder. So automated docking, right? This is there. So the script is there, configuration file is there. So process ligand means this ligands, right? So you that let's use the same ligands to dock, and the structure for this will be different, so we have to prepare this different receptor structure. Okay, configuration will also be different, so we will calculate the binding site, how we can generate the grid box information to be fed into this configuration file. Okay, let it predict. So the first one, they have predicted that this can be the active site pocket. Now if you open the second one also, they have predicted one more pocket here. You can see the volume of the pocket, surface area of the pocket, and some scores are given. So generally we will take the first with the drug score. Drug score is possible druggability. Okay, so the possibility that one drug can bind to this active site pocket that they have predicted. So pro most most of the time we take this the first option, but it is always not this in the case, okay, that the actual active site is the first uh, ranking the pockets. Okay, so you have to confirm if your pocket that you have predicted is the actual binding pocket. Okay, so you can show all the pockets, right? So none of them are having overlapping or near to the neighboring kind of pockets. So we have to decide which one we have to choose. So if we have to consider the score, the first one can be the binding site. So that's why it is always important to study about your target protein. So you have to look back and see which protein family does your uh, protein or the target belongs to, and what kind of uh, conservation they have, and if what kind of function they do. If they are cysteine proteases, so there should be a conserved cysteine residues that is present in the target protein, right? So what is that particular target or amino acid residue? That is the cysteine residue that is important for the catalytic activity, right? So if you go back, if you do a little literature search, you can see that cysteine 266. Okay, this is the catalytic residue that is important for the activity of this particular residue, particular target protein. Okay, so if the cysteine residue is in this pocket, okay, if the cysteine residue is uh, residing in this pocket, then obviously this should be the pocket that will be the active site pocket, right? So we have to see if the cysteine residue is present here or not. Okay, so one thing you can do is you can download this the whole thing. You can just press this download button and it will download all the pockets. Okay, and pockets in the sense the residues that are present in this pocket, so the residues that are making this pocket. Okay, we have downloaded this results. Let's copy this and let's create a folder now, name as binding site prediction. Oh, I have something binding site prediction. Okay, that's okay. So let me just delete this. So I've created a new folder named binding site prediction. Then I'm saving the output of that uh, doc scorer, doc site scorer. Okay, let's just extract this. Now if you open this and go to residues, you can see the residues, all the residues arranged according to the pocket. So pocket 0 is the first pocket, right? The highest scoring, this one, highest scoring pocket, right? So if you open this in the notepad, you'll see the amino acid residue numbers. Okay, so some cysteine are there. So good news. So cysteine are important for us. So cysteine is there. Okay, some atom of the cysteine also is making the active site pocket. Okay, one cysteine is there. If you look for the second one, so no cysteines are present, that means it cannot be the active site pocket, right? So the main purpose of the active site pocket was to have that catalytic cysteine residue, right? So that it can have some catalytic reaction and do the uh, that function for the target protein, right? So without the cysteine residue, that cannot be the active site pocket. Okay, so this you can rule out. And here also you can see that there is no cysteine residue, so this can be also ruled out. So no matter what kind of target you have, it should have a particular function, right? So for that particular function, you have to go back to literature and see which are the important residue that are performing that function, okay? Or what kind of domain it has, or what kind of motif it has. Some pattern will be there, so you have to find it out. But sometime we can also see in some papers, they'll just predict the active pockets, and they'll just take the highest scoring pocket, okay? And then do the further docking. It may be correct sometime, but it may not also be correct, because it doesn't, there is no rule that the first predicted active site pocket will be the actual active site pocket. Okay, so you have to some kind of correlate with some experimental data or some kind of report, okay, from literature. So let me just see what is the so here this is 16266, which is the real residue number. In our case, we have removed some of the residues from the N terminal. So in our model protein, it won't be this 266. Okay. So let me just open Maestro and see. So now the important thing is to find the cysteine protease, I mean the cysteine residue, which is playing an important role for this function of this particular target protein. Okay, so let me just see, open this and also verify. Here also one more cysteine is there. So what is this? Which one is this one? 4-1. Okay, the fourth one also contains the cysteine residue, the first one, and this fifth one. According to number, it is fifth one, but it is uh, according to this number that given by the doc site scorer, it is the fourth pocket. Okay, it also contains the cysteine residue. So let me see here also. So there is no cysteine residue. You can rule out this pocket. Okay, no cysteine residue. Okay, one more cysteine residue is there. Same cysteine residue with the fourth one. Okay, so we have this last one, this fourth one, and the first one. So let's see which cysteine residue is the catalytic one. Okay, so let's just open. Let's inspect visually, right? So let's change this. So here we have the template, okay, and then we have the predicted model. Okay, so this is the template, this is the predicted model. Let's overlap this to, okay, let's do an alignment or superimposition between these two protein. This is the template, okay, template in the sense because of that high sequence identity as well as coverage. When we search in the PDB database, we are able to pick this template, right? So they are homologous protein, right? So according to the sequence template based, that kind of search, if they are homologous, maybe this we can find out the if this contain inhibitor, we can see where the inhibitor is, and probably the cysteine residue will also be there if there is the particular active site pocket of this template molecule. So let's find it out. Let's see what I'm trying to say. So you have the predicted target molecule and the template, and if you go to this option, okay, text, you can see, you can type here alignment, okay, so you will be having protein structure alignment option here. So just click that option. You should select both the uh, I mean you should include both this structure in the workspace, okay, should be highlighted in this blue colors, and then okay, all the residues, that's okay, use the ASL, that's okay. So just click align. Okay, so if you see the RMSD value also, this is 1.5, that means they are very closely related. Okay, so I'll keep, okay, don't get confused, okay, I'm just trying to see if the uh, cysteine residue, because we have changed the number, we have deleted part of the N terminal, so the numbering will be different. Even though we are getting this number, the important cysteine residue number from the literature, but in our model the number will be changing. Okay, they must have changed when we built the model. Okay, so we are trying to confirm that which cysteine residue is the catalytic residue. Okay, all right, so this is, yeah, here you have this okay, this is different, this is not the catalytic residue. So disulfide bond is there, so this is not the one. And here you have the uh, that uh, ligand for the template, okay, for this template, and near to this you have the cysteine residues here. See, sulfur is there, means this are cysteine residue. If you hover over this, yeah, so this is for the template. You see that there is this, yeah, this is alpha 4 and this is the template one, CJW9. So here it will appear, okay, this one CJW9. So if I hover over this, cysteine number 42 is for the template, and if I go over here, so cysteine number 23 is for our target. And because the ligand that is present in the template is here in this region only, so this will be the it's catalytic residue. Okay, or otherwise if you want to do it properly, then you have to go back, take the whole protein sequence, count where we have deleted from where to where, and then see which number falls uh, like this 266. So you have to rewrite all the number of this target predicted molecule and then see which 266 is. Okay, otherwise you can just overlay with the template and see which is the cysteine residue that is important for catalytic activity. So when you say catalytic activity means your ligand should be in this particular pocket where the cysteine residue is. Okay, so in our case cysteine residue number 23 is the one. Okay, so if you go back to this pocket, predicted pockets, let's see which one is having yeah, so 1623 means the active residue, right? So pocket number first will be the uh, predicted, or actual predicted target. Okay, I mean actual predicted pocket. Okay, and if you see here, so this is 54, this is different, right? So maybe the cysteine which is involved in disulfide bond, maybe the this 53, I think. So if you look here, this is 20 and some other maybe there. Anyway, that's it. We have just identified, and we are, so when you write a paper, uh, now you can back up your prediction. Okay, so you are just not doing prediction and just taking the highest scoring pocket. Now you also have the proof or validation that this could be the active site pocket, because the active residue or the cysteine residue, which is important for that cysteine proteases function. Okay, so it is inside the pocket itself. So we have validated the prediction process, the active site prediction process. Okay, so once we have done this, the next step is to prepare the structure, and then uh, create that grid box around that active site pocket. Okay, so the same procedure will follow. So let's open this Autodoc tools. Now let's change this to part 2. What was that? Binding site prediction, right? Just here, and then make this default. Okay, and let's do one more thing. Let's copy the state homology models, right? This AlphaFold, let's copy that, this one, to binding site prediction. So let's open this file. Okay, so this is our model protein. So what is lacking in here is the hydrogen atoms or polar hydrogens. Then we need to add the charges also. Okay, so to do that we have to go to the edit option, edit menu, go to hydrogen, add hydrogen, polar only, click OK, right? And then edit again, charges, add Coleman charges, click OK. Fine, this is done. The now important thing is we have to define or see where the active site pocket is. Okay, so since we are going to do automated docking, so last time what we did was, in automated docking we did for uh, acetylcholinesterase, right? So to do this automated docking, we need the VINA this exe file, we need the receptor in the PDBQT format, right? The process receptor, hydrogen atom added, and then charge also added, right? And in the PDBQT format, we need the configuration file, right? And we also need this process ligand. Okay, let's not repeat the process ligand step. We can skip this one. We can just take the process ligand that we got from the previous step. Let's copy this and paste it in our binding site prediction folder. Okay, so we have the configuration file, we have the .exe file. We need to generate the process, I mean the receptor.pdbqt file first. Okay, so let's generate that. So in order to generate the pdbqt file for the receptor, you have to go to this grid option, go to macromolecule and go to choose option. Okay, choose this file, select and then click OK. Now you have the option to save this. Okay, this is our folder. Click save. Now you have generated the receptor in the pdbqt format, right? Only the receptor file. But we have to see where the active site pocket will be. Okay, so if you can just see that here are some disulfide bond, that means cysteine residues are there, cysteine residues are there, cysteine also is there. Most probably this will be the active one. Okay, so if you expand this and see cysteine number 23 right here, so if you just show this in a surfaced, cysteine 23. Okay, okay, it's somewhere here. So another cysteine is present here. Yeah, so it is here. Okay, this is cysteine, right? Another way to locate the whole pocket, we can only see the cysteine residue here, but the pocket, how big the pocket is, we do not know, right? This is a huge kind of opening, right? So still you can show the cysteine like this here or this one. Okay, and then what we can do is we can import or open the whole residues here. Okay, the first one, the first pocket, right? Open here. So this is the same coordinates. They have just extracted the residues which is making the pocket. Okay, so if you show here like this, so it's showing in the this uh, surface view. Okay, so you can see that this is the active site pocket that the tool have predicted, and the active residue is also present somewhere here. So now you can generate or create a grid box around here. You can do it manually, but why to do it manually, right? So you can calculate the centroid of this, all the residues that were predicted to make this pocket, and keep the centroid of that particular residues as a center point of the active site or the grid box, right? So the same procedure we can follow. So go to that residues that were forming the first pocket, then open this in the editor. Okay, copy this. Let's do the same process that we did from the starting. Go to Excel, paste it here, make it format proper. Okay, so let's calculate the average or the uh, I mean the centroid of each of the xyz coordinate, right? So go to average, press enter, and then scroll, drag this and see you get the xyz coordinate or the centroid of that residues that make up the active site pocket. Okay, so now you can fit the information in the grid box. Minus 9.97, right? So you can type minus 9.97 minus 4.69 minus 4.69, then minus 1.07, so minus 1.07. So see, it is perfectly fitting inside the pocket. Okay, so it's covering the whole pocket also, but you can increase the size. Okay, you can see after increasing the size how it is fitting, but I think it is enough. The pocket is completely enclosed. So now we can take this information. We are not going to do Autodock 4. We are going to do the automated docking. Okay, so we can take only this information, XYZ coordinate information, and the dimension of this grid box. And now we can go back, and here I have copied the configuration file from the previous docking study. Okay, so you have to change this. Okay, so let's change the coordinate here. For us now we need this coordinate, right? Let's copy this and paste it here. This is the x coordinate, y coordinate now, and this is the z coordinate. The dimension is the same, 40 40 40 you can give, and we have to change the this name of the receptor also. Here name of the receptor is this dot pdbqt. Okay, so we have set up the uh, grid box where we have to do the docking. Okay, so this is now a proper targeted docking. uh, the pockets predicted by a tool known as the uh, dock site scorer. And now we are going to do automated docking of this particular target protein and using this ligands. Okay, this ligand also I have copied from the previous run. Okay, so where was the previous run? This one. So this is the output of processing the ligand from the previous run. So I'm using the same ligand that we have done for acetylcholinesterase, keeping it here. So let's use this for the cysteine protease, that is pepsipin. .exe file is there, configuration file is there, receptor in proper format, and the ligand file from the previous run is also there. So now we can do docking. So let's open Anaconda first. Then open this Jupyter notebook. So somewhere I've already opened the script, right? So here is the script. Okay, so we need to change the path. So let's copy our path here and then paste it here. Should be forward slash. Okay, and then run this. So I think it's working. So we are in this path now where our files are stored. Okay, so let's skip this ligand processing step because we are taking the ligand instead where we did docking for the last example. Okay, and then use this, right, the final docking one. So here we don't need to change anything. So we are taking the ligand from this process ligand folder. Go back. We are taking the ligand from this process ligand. So these are the ligands which are properly processed in PDB-QT format, properly charged, hydrogen added. So you don't need to do anything for this. And then, okay, the configuration file is there, receptor is there. So it should probably run properly. Okay, so let's click here. So this black circle means it is running. Okay, it's busy. So a new folder will be generated, dock out, and if you click open here, it is docking. So here we have model a protein. The structure was not there. Then we predicted the active site pocket. So after predicting the active site pocket, we are doing docking using the predicted pocket. Okay. Kamlesh, are you able to follow? John, you guys are there? You guys following? Okay, so you have to, practice, practice, practice. Okay, that's the only solution. So from the starting, you have to practice, and when you encounter this kind of study, like this kind of research that you have to do, then obviously you will have to look how you can do, and these are the steps you have to follow. So look here, you can always look up the recorded video and just can try to follow. Okay, and later on if you have problem in the steps, you can always contact me. So these are the predicted activity or the binding affinity, okay, for the ligand molecules. So let's extract again and convert it into SDF format, right? So click open, it's converted. So let's go back. So this is 6 minus 6.50 is the highest one. Okay, so let me just import this in Maestro, the results. Okay, so top dog molecule, right? So all this import. So if you go for this, it's here, and let's also show the template and let's see how they are. Okay, so it's a bit different from the template, and of course if we keep the uh, after superimposing, you see at this position, if you do sequence alignment, you can also see there is a drastic change in the amino acid residues here. So here it is 234 as spotted, I think, and here is phenylalanine. Okay, these two are totally different residue. So in the case of the template structure, it has changed. Okay, so using this also you can do evolutionary study kind of thing. Okay, you can look at why this particular drug molecule is working for this organism and not for the other. So you can also do evolutionary study also. Anyway, for us it's showing it the active site pocket, so we will be interested in the, now we have done just 12 or something molecule, but if you ask me, I will be interested in the molecule which comes near to the this particular active residue, cysteine residue. So this particular residue or this particular molecule that we have docked is far away, but still it is a pocket. Pocket is huge, so it's still a pocket. But I will be uh, looking for molecule which can block the entry of the substrate to this particular active residue. Okay, the cysteine residue. So we can look for only for we this kind of conformation at that particular position, as well as having the molecule the with the particular position with high binding affinity. Okay, okay, so it is somewhat near to the, here it may block, right? So this, if the the binding affinity is high, then we can consider this one also. So like that we can select, we can choose, and when you choose something, it should not always be, absolutely based on the scoring binding affinity. Okay, it should be logical. We have to should be able to, say that I'm choosing this one because it is near to the particular residue, or it may be blocking the active site pocket. If it is channel, then you have to see where the entry point and where is the catalytic residue, and if it is able to have interaction uh, around the catalytic residue, then it's quite okay. All right, this is how you can do. Okay, so let's generate a nice uh, high quality image. Okay, so here we may not be getting a nice interaction. Let me just see. To get a high binding affinity and then interaction at the active site pocket properly with the particular residue that you want, you have to do docking large number of molecules. Okay, and then see what are the top scoring molecules, and then see their interaction also, how they are interacting. So you cannot just randomly pick high scoring molecule and take that, tell that this can be the particular or this can be the molecule that can inhibit the target protein. Okay, so you have to be rational and you have to be able to answer why you are taking that. Pretty far away, so we need to do more docking to get that particular molecule. Okay, I would prefer a molecules binding somewhere here. Okay, be different. Somewhat okay. Can see what kind of interaction is having. Some pi-pi interaction is there, but hydrogen bond interaction won't be there because we haven't added hydrogen bond in the this structure. So let's add hydrogen bond and see. Okay, this is somewhat near. See the interaction. So pi-pi interaction here. Some hydrogen bond interaction also is present. All right. So if you want to generate a proper kind of 3D image, okay, then it depends on how you want to present. Okay, so there is no thumb rule. So I would I would like to highlight the ligand. So if you click here, that means it is selecting the ligand. So where is that? This one, right? So you can change the ligand representation. You can keep it as ball and stick. Okay. So if you want to highlight it more, then you can change the color also. So let's keep something like green, something kind of, so that it can highlight more. Okay. And then you can change the background of this, right? And so we cannot see the interaction right now. I mean in 3D representation. So you just have to, there is some kind of button here, so you have to keep it on the on state. Okay, so if you show this properly, we can remove this classes and then yeah, that's it. So there are two hydrogen bond interaction and one pi-pi interaction. So if you change this to residue, that means you are, when you want to select from this uh, workspace, you can select a residue or chain or molecule. Okay, for now let's select residue because I want to highlight the residue which is having interaction with the ligand. Okay, so you can click shift button and then click the residue, and then this one also, 3 residue I'm selecting, right? And this one, yeah, I selected wrong one, correct only. So now I've selected the 3 residues and I want to hide all other residues. Okay, so you have to hover over this particular selection and do a right click and then say invert selection. Okay, so all the other residues are selected. Then you can just go in this current selection option, click in the pane button and select this eye kind of thing. Okay, eye symbol is there, right? So when you select this, everything else is hidden except for the three this residues that were showing interaction. Again, you can select this three and you can represent this in another format, okay, or another representation you can do so that it can be highlighted. Okay, so this is another representation and you can show the ligand again. So now we have only the interacting residues and the ligand, right? And again we can show the protein in a different kind of representation. We can show in a cartoon format. Okay, when you do cartoon format, it is shown like this. Okay, or otherwise you can choose different representation of the protein. So you can go for like this CA, that is alpha carbon traced, and okay, why it's showing both the thing, should not be showing both the thing. Anyway, let me just try to change again. Okay, 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 okay. Oh, oh, I'm so sorry. So here the problem is it should not be showing the both the representation at one go, I mean one time. Okay, so this is alpha fold. If I do hide, okay, it's not hiding also. Something is wrong. Okay, I think I need to restart, but let's not do that right now. Let's skip this representation itself. Okay, so let's skip the, which one was that? Ah, this is why we are loading both the protein. That's why one original protein is there without the hydrogen atom, and after preparation one more protein is there. So this is the one. Yeah, great. And the ligand molecule, where is the ligand molecule? Great. This one only. So now you can show something like this, right? You can take a picture here. I mean the snapshot kind of thing. You can save the image here. Let's do a proper way. Yeah. So what I want to do is cheat. 1 second, okay? So I would like to create uh, this figure is something like this, okay? So in when you do publication and all, so it's look nice to have this kind of uh, figures, okay? So just you are trying to show the whole structure, and also you are trying to you know uh, uh, magnify or enlarge the region where you can see the interaction also, like this interaction is there, like this you want to show. So what we can do is we can do the same thing. We can show one the full protein ligand structure like this. So we can take one image here, right? You can save it as JPEG. Let's say protein ligand. Right? And then one more, you can enlarge this, show the proper interaction. Okay, can see, right? This two hydrogen bond interaction, one pi pi interaction. This you can take as another snapshot. You can say this one is enlarged. So now you can use what this Canva, okay, the free version of Canva. So you say design, create a design. So this is a free version, okay, not pro version. After saying that create a design, you go for this custom size, okay. So let's go for inches and make the figure larger, okay, 14 to 14, and then create new design, right? So what we can do is we can just upload that particular file, okay. Go to upload, and then binding site, right? And then this first. So you can crop easily here. Then you can enlarge also. Okay. Then another thing is you have to upload the other one also, enlarge one. Okay, then go to element. Okay, this element option, and then search for flat circle shape. Press enter and use this one. This is also free. Okay, I mean they are not, these are pro, that means you require license. So if the this icon is not there, means it is free to use. Okay, so create something, place somewhere this level with the this particular active site region. Done, right? And then go again to the upload option. So this is the enlarged one that you have just uploaded. Click here, and when you move this to the this circle, he will automatically take in the molecule. Okay, I mean the image. But you see, even though it is circle, we cannot see the border, right? So click here to the image and click to this border style. Okay, and you can make it dotted lines, but let's not do that for now. So now you have created a line here, border, and it look enlarged, but you need to level this, right? So this one is what? This is phenylalanine 135. Okay, go to text, add text, and then you can type it here, PHE 135. Okay, you can reduce the size 23, like that you can do. Okay, make it bold. This is fine, I guess. And what is this? You can duplicate this. And another is what? Let's see this one. This is glycine 18. Okay, so another one is gly 18. One is what? Tryptophan 177. So another one is tryptophan 177. TRP 177. Okay, this is glycine. This is phenylalanine. And this is tryptophan. So it's look good, right? And then we need one more circle here, right, to make, to tell that this is the area where you are enlarged, getting it enlarged. Okay, so again let's go to element and type here circle shape outline. Okay, press enter. So these are license, means you need to pay license for this to use circles. So another free one is here, so you can use this. Okay, right, so now we have created a, I think I need to move this little bit. Right, this is fine picture, and then you need to place the this lines. Okay, so all the lines I've checked to make it angle, not it's like paid one, so we have a workaround, don't worry. So let's do one thing. Let's save this first. If you want to save this, you have to go to the share option, then go to download, and you cannot increase the size. That's okay. So you just click download. So it's been downloaded. Copy this. Let's paste it in our working folder. What is that binding site? Right, so let's go to one more option, one more program, that is Paint. Open the file or the image that we have just generated. Okay, it's a huge file. Okay, not this one. Then this one, right? So you use this particular line, okay, line option. Then let's zoom in and then do this from here to here. Okay, and another here.
Sir,
Yeah,
so what is the name of this app, sir, to draw the line within the
it's
circle?
Paint. It's in the Windows system itself. Paint.
Oh, Windows 10 itself.
Paint. Windows Paint. Okay.
Windows Painter, sir.
Yeah.
Is Windows itself having this
Yeah. Yeah.
kind
Yeah.
of facility, sir?
Yeah. Yeah.
Oh, okay,
So
okay.
inside Windows itself, you have this software. I'm using all open source only. Okay.
Okay, sir.
So now you have the proper uh, presentation. Okay. I mean proper image. So now you can save this. Go ahead and save this. And let's say this is figure.jpg. Okay. So if you go to the working folder, we'll be getting a figure here. Okay. So it's finally done. But if you go and see the properties, okay, so here you can see in detail we have this 143 dpi, means this is the resolution. Okay, so most of the journals, they have some specification for submitting the figure, so they will ask for like 350 dpi or something like that. Okay, 350, 300, like that. So here also we have some other ways to do that. So I forgot the name of that DPI converter, right? Yeah, this one. So this will help you to change the DPI. Okay, so let's keep 300. Choose your figure. So this one, click open, and it's downloaded, right? So let's copy this, paste it here. Same figure. Okay, no changes, but the resolution will be increased now, so that you can submit to your I mean journals if you are looking for publication. So now this is 300 dpi, right? So accordingly you can increase the dpi. All right, so everything is done. Now it's look proper. You can change according to your style. Okay, so if you want square also, yeah, the square option is also there in Canva, so you can make it square. That's it. So we have come to the end. So if you have any
Sir,
question, you can ask. Yeah.
sir, how can we interpret the result for this docking picture when we write it for publishing the paper?
So
So can
interpretation
you send me
again.
the any can you send me any for model already uh, written as a result for the document
Okay, okay.
picture?
I can send you papers. That's no issue. Published paper, right?
Okay, sir. Yes, yes, sir. Already published paper by you.
Yeah, yeah, yeah. I can
Uh,
send you. That's not a problem. So again, I'm telling you, it depends on your work that you are doing. Okay. So like
okay, sir.
here in this case, I was looking for no, this is not a proper inhibitor. Okay. I'm just for the sake of showing, I'm showing this inhibitor in this case. Okay. But the inhibitor I'm looking for should it should be close to the particular cysteine residue, which is the active or catalytic residue, or if it is able to bind or have interaction with the cysteine residue, this is more than enough. So, and it should have high binding affinity. So those I have to check. Okay, and if your target is different, then obviously your objective will be again different. So it depends on your target protein and what you want to study. And if you're looking for some natural product, so those natural product with the high binding affinity and what kind of interaction that you are preferring for that particular target, again, that depends on what you are looking for. Okay.
Okay, sir.
So, right. So if you have problems, you can always connect with me. Okay. You can make a
Of
video
course, sir.
or you can make a screenshot and send me the error if you have errors while performing the steps. But do practice, and we also do free workshops. So tomorrow we are going to do a pharmacophore based screening. Okay. So it's a
Okay,
free
sir.
workshop. You
Sir,
can join.
whenever you conduct the free workshop, please share the details, sir, please, sir.
Yeah, yeah, sure, sure. I will put it up in the group also. No
Okay,
issue.
sir. Please store my number whenever such kind of workshops and
Yeah,
other
yeah,
practice sessions. Please inform, sir. Please, sir.
sure, sure. No
Tomorrow
issue.
at what time, sir?
7 p.m. Start from 7
Okay.
p.m. and 3 hours workshop.
Okay, sir. Please send me the details, sir.
Sure, sure.
Okay, sir.
Okay,
Thank you, sir.
okay. So we'll meet up some other workshop, okay, in some other workshop. Hope to see you
Okay,
again.
sir.
Okay. Thank you all. Bye bye.
Thank you, sir. Thank you, sir.